Semiconductors are materials that have electrical conductivity between that of a conductor and an insulator. This unique property makes them essential in the field of electronics. One interesting fact about semiconductors is that they are the foundation of modern technology, powering devices such as smartphones, computers, and solar cells. Without semiconductors, our world would look very different. In terms of numbers, the global semiconductor industry was valued at over $400 billion in 2020, highlighting the significant economic impact of these materials. Another fascinating detail is that the first semiconductor device, the point contact transistor, was invented in 1947 at Bell Labs, revolutionizing the field of electronics. Today, semiconductors are used in a wide range of applications, from microprocessors in computers to power electronics in electric vehicles. The conductivity of semiconductors can be modified through a process called doping, where impurities are intentionally added to the material to change its electrical properties. This process allows for the creation of both N-type and P-type semiconductors, which are essential for building electronic devices. Intrinsic semiconductors, such as pure silicon or germanium, have an equal number of electrons and holes, resulting in limited conductivity. Extrinsic semiconductors, on the other hand, have been doped to increase their conductivity. The band theory of solids explains the behavior of electrons in semiconductors, showing how energy levels form bands that determine the material's electrical properties. Understanding these principles is crucial for designing efficient electronic devices. In conclusion, semiconductors play a vital role in modern technology, and their unique properties have paved the way for countless innovations. By harnessing the power of semiconductors, we have been able to create the advanced electronic devices that have become an integral part of our daily lives. Intrinsic and extrinsic semiconductors are two fundamental types of semiconducting materials that play a crucial role in the field of electronics. Intrinsic semiconductors, such as pure silicon or germanium, have a balanced number of electrons and holes, resulting in limited conductivity. On the other hand, extrinsic semiconductors are doped with specific impurities to enhance their electrical properties. One interesting fact is that the conductivity of intrinsic semiconductors can be significantly increased by doping them with elements from group 3 or 5 of the periodic table. For example, adding phosphorus to silicon creates an N-type semiconductor, while adding boron creates a P-type semiconductor. This doping process allows for the precise control of the electrical behavior of semiconductors, enabling the design of complex electronic devices. In terms of numbers, the global semiconductor market for both intrinsic and extrinsic semiconductors was valued at over $400 billion in 2020, reflecting the immense economic impact of these materials. Another interesting detail is that the development of extrinsic semiconductors has been a key driver in the advancement of semiconductor technology, leading to the miniaturization and increased performance of electronic devices. The ability to tailor the electrical properties of semiconductors through doping has revolutionized the electronics industry, enabling the production of faster, smaller, and more energy-efficient devices. Intrinsic and extrinsic semiconductors each have their unique characteristics and applications, with intrinsic semiconductors serving as the foundation for doped extrinsic semiconductors in electronic circuits. Understanding the differences between these two types of semiconductors is essential for engineers and scientists working in the field of semiconductor technology, as it allows for the optimization of device performance and functionality. Doping is a process used to modify the electrical properties of semiconductors by intentionally introducing impurities into the crystal lattice structure. One interesting fact is that the most commonly used dopants in silicon are boron and phosphorus, which create P-type and N-type semiconductors, respectively. Doping allows for the precise control of the carrier concentration in a semiconductor, which is crucial for designing electronic devices with specific performance characteristics. In terms of numbers, the concentration of dopants in semiconductors is typically on the order of parts per million to parts per billion, highlighting the precision required in semiconductor manufacturing processes. The doping process can significantly impact the conductivity and charge carrier mobility of a semiconductor, influencing its overall performance in electronic circuits. Another interesting detail is that the concept of carrier concentration refers to the number of charge carriers, electrons or holes, present in a semiconductor material. The concentration of carriers can be controlled through the doping process, with higher dopant concentrations leading to increased carrier densities. This, in turn, affects the conductivity and resistivity of the semiconductor material. Understanding and controlling carrier concentration is essential for optimizing the performance of semiconductor devices, such as transistors and diodes. In the field of semiconductor technology, precise control of carrier concentration is critical for achieving desired electrical characteristics and device functionality. The ability to tailor the carrier concentration in semiconductors has enabled the development of advanced electronic devices with improved speed, efficiency, and reliability. Overall, doping and carrier concentration play a vital role in semiconductor manufacturing and are key factors in the design and performance of modern electronic devices. The band theory of solids is a fundamental concept in condensed matter physics that explains the behavior of electrons in solid materials. One interesting detail is that the band theory describes how electrons in a solid material are distributed among energy bands, which are ranges of allowed energy levels. These energy bands can be either filled with electrons or empty, depending on the material's electronic structure. An intriguing fact is that in a solid material, the outermost electrons of each atom interact with neighboring atoms to form molecular orbitals, leading to the creation of energy bands. The energy bands in a solid can be classified into two main categories: the valence band, which contains electrons at their lowest energy levels, and the conduction band, which is empty or partially filled with electrons at higher energy levels. The energy gap between the valence and conduction bands, known as the band gap, determines the material's electrical conductivity. Materials with a large band gap are insulators, while those with a small band gap or overlapping bands are semiconductors or conductors. In terms of numbers, the band theory has been instrumental in the development of semiconductor technology, with the global semiconductor market valued at over $400 billion in 2020. The ability to manipulate the band structure of semiconductors through doping and other techniques has revolutionized the electronics industry, enabling the production of advanced electronic devices. Another interesting fact is that the band theory also explains phenomena such as electrical conductivity, optical properties, and thermal behavior of solids. For example, the movement of electrons between the valence and conduction bands is responsible for the electrical conductivity of materials. Additionally, the absorption and emission of light by solids are governed by the energy band structure, leading to applications in optoelectronics and photonics. The band theory of solids has provided a theoretical framework for understanding the electronic properties of materials and has paved the way for numerous technological advancements. Understanding the band structure of solids is essential for designing new materials with tailored electronic properties for specific applications. Researchers continue to explore novel materials and band engineering strategies to push the boundaries of semiconductor technology and develop next-generation electronic devices. P-N junctions are formed by joining a P-type semiconductor with an N-type semiconductor, creating a boundary known as the depletion region. One interesting detail is that the P-N junction acts as a diode, allowing current to flow in one direction while blocking it in the opposite direction. This property makes P-N junctions essential components in electronic circuits, serving as rectifiers, switches, and signal modulators. An intriguing fact is that the operation of a P-N junction diode is based on the movement of majority and minority charge carriers across the junction under the influence of an applied voltage. When a forward bias voltage is applied across the P-N junction, the depletion region narrows, allowing current to flow through the diode. Conversely, when a reverse bias voltage is applied, the depletion region widens, preventing current flow. In terms of numbers, the global diode market was valued at over $10 billion in 2020, highlighting the widespread use of diodes in various electronic devices. Diodes are used in applications such as power supplies, signal processing, and communication systems, demonstrating their versatility and importance in modern technology. Another interesting fact is that PN junction diodes exhibit unique electrical characteristics, such as forward voltage drop and reverse leakage current, which are crucial for determining their performance in circuits. The forward voltage drop of a diode is typically around 0.7 volts for silicon diodes, while the reverse leakage current is on the order of nanoamperes to microamperes. Understanding these characteristics is essential for selecting the right diode for a specific application and ensuring proper circuit operation. The development of PN junction diodes has been a key driver in the advancement of semiconductor technology, enabling the miniaturization and increased efficiency of electronic devices. Researchers continue to explore new materials and design techniques to enhance the performance of diodes and push the limits of electronic functionality. The integration of PN junction diodes into integrated circuits has revolutionized the electronics industry, leading to the development of complex digital systems and high-speed communication networks. The unique properties of PN junction diodes, such as fast switching speed and low power consumption, have made them indispensable components in modern electronics. As technology continues to evolve, the demand for high-performance diodes will only increase, driving further innovation in semiconductor device design and manufacturing. Transistors are semiconductor devices that serve as amplifiers and switches in electronic circuits. One interesting fact is that the first transistor was invented in 1947 at Bell Labs, marking a significant milestone in the history of electronics. Transistors revolutionized the field of electronics by replacing bulky vacuum tubes with smaller, more efficient solid-state devices. In terms of numbers, the global transistor market was valued at over $15 billion in 2020, highlighting the widespread use of transistors in various applications. Transistors are essential components in amplifiers, allowing for the amplification of weak signals in audio, radio, and communication systems. Another interesting detail is that transistors can also be used as switches to control the flow of current in electronic circuits. By applying a small signal to the base of a transistor, it can act as a switch, turning a larger current on or off. This property is crucial for digital logic circuits and power control applications. The development of transistors has led to the miniaturization and increased performance of electronic devices, enabling the creation of smaller, faster, and more energy-efficient products. Transistors come in various types, including bipolar junction transistors, BJTs, and field effect transistors, FETs, each with its unique characteristics and applications. BJTs are commonly used for high-power applications, while FETs are preferred for low-power and high-frequency applications. Understanding the operation and characteristics of transistors is essential for designing electronic circuits with optimal performance. Researchers continue to push the boundaries of transistor technology, exploring new materials and device structures to enhance transistor performance and enable new functionalities in electronic systems. Metal oxide semiconductor field effect transistors, MOSFETs, are key components in integrated circuits, enabling the miniaturization and high performance of electronic devices. One interesting detail is that MOSFETs consist of a gate, source, and drain, with a thin layer of oxide separating the gate from the semiconductor channel. This design allows for the control of current flow through the channel by varying the voltage applied to the gate. MOSFETs are widely used in digital circuits, power amplifiers, and switching applications due to their high efficiency and fast switching speeds. In terms of numbers, the global MOSFET market was valued at over $6 billion in 2020, reflecting the significant demand for these devices in various industries. MOSFETs come in different types, such as enhancement mode and depletion mode, each offering specific advantages in terms of performance and power consumption. Integrated circuits, ICs, are complex assemblies of interconnected electronic components, including transistors, resistors, and capacitors, fabricated on a single semiconductor substrate. An interesting fact is that the first integrated circuit was developed in 1958 by Jack Kilby at Texas Instruments, leading to the modern era of microelectronics. Integrated circuits have revolutionized the electronics industry by enabling the mass production of compact and reliable electronic devices. In terms of statistics, the global integrated circuit market was valued at over $400 billion in 2020, underscoring the pervasive use of ICs in consumer electronics, automotive systems, and telecommunications. The continuous advancement of IC technology has led to the development of system-on-chip (SoC) solutions, integrating multiple functions on a single chip for enhanced performance and efficiency. As the demand for smaller, faster, and more energy-efficient electronic devices continues to grow, the role of MOSFETs and integrated circuits in driving innovation and technological progress remains paramount. Semiconductors have had a profound impact on the electronics industry, driving innovation and shaping the modern technological landscape. One interesting detail is that the invention of the integrated circuit in the late 1950s paved the way for the development of increasingly complex electronic devices, leading to the rise of the digital age. This breakthrough allowed for the integration of multiple electronic components onto a single chip, revolutionizing the way electronic systems are designed and manufactured. In terms of numbers, the global semiconductor industry was valued at over $400 billion in 2020, highlighting the immense economic significance of these materials. Semiconductors are the building blocks of modern electronics, powering devices such as smartphones, computers, and medical equipment. Another fascinating fact is that the continuous miniaturization of semiconductor components has enabled the production of smaller, faster, and more energy-efficient devices. This trend, known as Moore's Law, has driven exponential growth in computing power and has fueled advancements in artificial intelligence, data processing, and communication technologies. The impact of semiconductors extends beyond consumer electronics, playing a critical role in sectors such as automotive, aerospace, and healthcare. Semiconductor technology has enabled the development of advanced driver assistance systems in vehicles, satellite communication networks, and medical imaging devices, transforming industries and improving quality of life. As the demand for high-performance electronic devices continues to grow, the semiconductor industry remains at the forefront of technological innovation, driving progress and shaping the future of electronics. One interesting trend in semiconductor technology is the development of new materials such as gallium nitride, GaN, and silicon carbide, SiC, which offer higher efficiency and power handling capabilities. These materials are increasingly being used in power electronics, automotive systems, and renewable energy applications. In terms of numbers, the global market for GaN semiconductors is projected to reach over $1 billion by 2025, driven by the demand for high-speed and high-frequency devices. Another emerging trend is the adoption of 3D integration techniques, where multiple layers of transistors are stacked on top of each other to increase performance and reduce footprint. This approach enables the creation of more compact and energy-efficient devices. Additionally, advancements in quantum computing and neuromorphic computing are pushing the boundaries of semiconductor technology, opening up new possibilities for computing and artificial intelligence applications. The semiconductor industry continues to drive innovation and shape the future of technology. Emerging trends such as the development of new materials like gallium nitride, GaN, and silicon carbide SiC are revolutionizing power electronics and renewable energy applications. The global market for GaN semiconductors is projected to exceed $1 billion by 2025, highlighting the growing demand for high-efficiency semiconductor devices. Additionally, three-dimensional integration techniques are enabling the creation of more compact and energy-efficient devices by stacking multiple layers of transistors. The adoption of quantum computing and neuromorphic computing is pushing the boundaries of semiconductor technology, opening up new possibilities for advanced computing and artificial intelligence applications. These advancements underscore the importance of ongoing research and development in the semiconductor industry to meet the evolving needs of the digital era and drive technological progress.